Welcome to the Lecture 9 Q&A. Here we go. The question was about what's going on with inverse cascade, and would looking at it in Python Tutor help us understand it? I'm guessing not. I mean, you could try, but most recursion problems are best understood by just understanding what the pieces do and how they fit together, rather than trying to trace through it. Because as soon as you make the argument just a little bit bigger, then tracing through it becomes yet more complicated. And so the goal here, this was like an exercise within one of the videos, was to create this pattern. It should be the case when your goal is to print a bunch of stuff that the code corresponds to printing parts of it. So this call to grow, when n is 1, 2, 3, 4, corresponds to printing all of that. And this call to shrink corresponds to printing all of that. And what do we leave out? Oh, well, we need to print 1, 2, 3, 4. Oh, and we have a line to do it. So that kind of explains this implementation, except for that we don't know what grow and shrink do, and they're defined in this kind of complicated way. But this complicated way isn't actually that complicated if we try to unpack it. So it says grow involves taking in a number, which at the beginning would be 1, 2, 3, 4. I think it's helpful to think about examples, and then calls one function and then calls another function. F then G checks to see if n is not 0, and if so, it calls F and then G. And then we see what the F and the G are. Well, they're grow and they're print. And the n that we pass in is not 1, 2, 3, 4, but instead 1, 2, 3. So if I had like rewritten grow without this higher order function business, it would have just looked like grow n divided by 10, print n divided by 10. That's what do f and then do means, except that these are both checking that if it's the case that n divided by 10, and this in Python just means if this is not equal to 0. That would be equivalent to write either one. In fact, a quirk of Python is that the sort of standard style guide says you should leave this part out. I think it's fine to leave it in as well, because it makes it more explicit. But in any case, this is the grow function that you construct by taking in a number n, then calling f then g, which checks to see if n divided by 10 is not 0, and if so, calls f, which is grow, and then g, which is print, in order to do the work. So in this alternate definition, it still works. So I guess that's how I would suggest understanding this example, is that you're using the power of higher order functions in order to write grow and shrink in a way that is a little bit more succinct by having a function that does the thing that they have in common, which is basically like check for a base case, call one function on n, then call some other function on n. But grow involves calling grow first and then printing, whereas what would shrink look like? Well, if we look at the definition, it says first print and then shrink. That works, and then we could get rid of all this stuff. It's not doing anything anymore because these are being redefined.
So let me add a couple things to this. So I want to re-emphasize that often when you code, and I still do this to this day, I start with sort of maybe a little clunky, a little long, but very explicit, concrete implementation. I make sure it works, I make sure I understand it. So for example, if I was doing this, I would start with the ladder of these functions where I explicitly define the functions. It's a little bit clearer. It's a little clunky. You can see you need a lot more code. And then once you've got that, then I can start tightening it up and writing efficient code and doing the lambda expressions. And the reverse works. When you're trying to understand something, you know that a lambda function is just a shortcut for a defined function. So rewrite it as the defined function. It's often clear because now you're dealing with these sort of dual complexities. You've got the lambda expressions, the anonymous functions, and you've got this new concept of recursion. So removing complexity by just unpacking that lambda is a good way to do it. I'm also going to reemphasize that I don't think for a lot of the recursion examples, the environment diagrams are the best way to do it. I think the better way to do it, as John was saying, is to look at the code, think about the tree diagram of the recursive calls. You can sketch these things out. I call this, I call this, I call this. I think that's a little bit more compact than trying to track these huge environment diagrams with all the variables.
And there was one question in the chat about how come this is just if n, whereas this has a not equal to 0. And you could remove this. 0 is a false value in Python, meaning that if you say if and then a number, if that number is 0, then it will not execute the suite of the if statement. If it's anything other than 0, then it will. So this would do the same.
In Python, you can actually just put in, it doesn't have to be an equality or inequality check. You can just put in a value. And so they're now asking, so there's no base case.
Great question. So where would the base case be? Think about that.
Yeah. So there's sort of a base case here. It's just not explicit.
Yeah, so you kind of say nothing to do. I think that's the base case, is that you just kind of return. It would be a fine way to write it. So if you wanted to kind of break it out into base case and recursive case, the only action happens in the recursive case, and the base case, you don't do anything else.
Yeah. So the base case just says stop. So if you have a conditional in there, where the result of the conditional, I think
we've broken it somehow.
I think you got it backwards. It should be if not. Yeah. Yeah, there it is. So if there's no conditional, you're probably going to have trouble, right? Because that means it's going to keep recursing. You got to have something that says only do this under certain conditions. And if that certain condition is not met, well, then there's nothing to do. So you're done. Now, in this case, in some of the other base cases like Fibonacci, we had to do something. We had to return 0 or 1. But here, there's just nothing to do. We're done. We just stop working. Yeah. So there is an implicit base case. And I think this came up in the lecture too, is I probably would have written it like this with the explicit base case, just so I can see it. It was per April's question. Is I just want to see that it's there so I don't have to infer it. Yeah.
Yeah, I mean, the point of this example is not to say this is the right way to define this function, because I think it would be much better written like this. But the point of this example was to show that it is certainly possible to have sort of implicit base cases where you only define what to do in the recursive case, where you could use higher order functions where the base case is like inside this higher order function and it's not here. All of the things that we've learned so far in the class can be mixed in with recursion. Doesn't mean it's a good idea, but it's worth knowing that that's possible. Sure, good question. So the question was about count partitions, which was an example from lecture, and what's with the with m and the without m and these recursive calls. With every tree recursion problem like this one, where you're taking a problem and you're solving it with kind of smaller instances of the same problem, I do think it's very important that you understand what you're trying to get done before you start reading the code. Like reading the code just isn't very helpful unless you know what you're trying to simulate. And what we're trying to simulate here is if you're going to write the number n as an expression of adding up a bunch of different numbers that are all m or smaller, then it turns out there's a way to split that whole group of things that you're counting into two smaller groups. Okay, so in this case, the two smaller groups, well, let's just fill in the values. They're, if we started with 6, 4, they would now be 2, 4. And they would be 6, 3. Now, adding up to the number 2 using positive numbers up to size 4, well, you can't really have a 4 in there, or you're going to have a sum that's bigger than 2. So this is actually equivalent to just if we had written 2, 2, assuming we get our base cases right. So basically we're saying if you want to write a sum of size up to 6, what you should really do is figure out how you sum up to 2. And why is that relevant? Well, one way to get 6 is to use a 4 and then have some other expression that adds up to 2. And in fact, there's like 2 different ways to do it. You could write it that way, or you could write it that way. But this part is represented by this recursive call, where with m describes that what you're really counting is expressions that start with the number m, which in this case is 4, if we're looking at this example. So definitely think about an example when you're trying to analyze what one of these does, and make sure that you know what you're counting, if you're counting, or what you're trying to find the maximum of, if you're trying to find the biggest thing, or whatever. And in this case, we're counting up expressions that look like this, and we're using ones that have a 4. I think in the lecture description, I said that these need to be in increasing order. So let's just put the 4s at the end so it doesn't make it even more complicated. Okay, and then what about without m? So this says count up all the ways of summing to 6 with parts up to size 3. Well, that's because we're not adding a 4. And so we have to get all the way to 6. But we'll do it with parts up to size 3. And we're not adding 4 at the end, right? So there might be one like that, and one like that, and etc. All of these down here are going to be counted by this recursive call. If you count up all of these, and you count up all of those, and you add them together, then you get the count of all the ways of getting to 6 using parts up to size 4. Where you either used a part up to size 4, or you did.
So let me add 2 things here, if I may. So one of the hallmarks of recursion is that you sort of break the problem down into subproblems, and those subproblems tend to be simpler. Yeah. So in this case, for example, we are looking for all partitions of 6 with the maximum number is 4. And there's this really beautiful graphic in the lecture that John showed, where he showed you all the possible answers. Yeah. And what you saw is that there's a set of those answers that have a 4 in it. Yeah. So that's the with 4 recursive call. So tell me how to get to 6 if I'm telling you one of the numbers, if the maximum number is 4. Yeah, this is it. And then look at everything below that. There's no 4 in it. Yeah, so if you look at the first 2 lines here, 2 plus 4 is 6. 1 plus 1 plus 4 is 6. Those are the only 2 ways that you can get to 6 where one of the numbers is 4, right? You can see that, of course. Now, everything below that, it's as if we had asked to solve a completely different problem. Well, not a completely different problem, a smaller problem, which is how do I get to 6 where the maximum value is 3? And let's agree that since 3 is less than 4, that is part of the solution to the first problem. So all we've done with the with 4 and the without 4 is we've split the solution space here into 2 sets, one that include 4, one that don't include 4. And then we do it again. So then below, there's the solutions that include 3 and don't include 3. And then there's the ones that include 2 and don't include 2. And notice that we keep simplifying the problem. Yeah. So that's the elegance of recursion, is that you sort of peel off a little bit of the problem that's easy to solve. You know, it's almost like the base case. And then everything else you just do, well, recursively. You just sort of jump off the cliff, say that you're going to do it, and it happens. So that's what those 2 things are right there.
If this takes a while to sink in, like that is very normal. You know, you might get up to this point in the course and think like, isn't computer science really about just learning all the rules and then like applying them and maybe looping through stuff? But it turns out that computer science is broader than that. It's really about solving all kinds of problems using computation. And this idea that you could use things you are building in order to build bigger things comes up over and over and over again. And it's a different way of thinking. And yeah, one of the trickiest parts is that you need to relate the code to what in the world you're representing. That's where how most like interesting programs work, is that you're representing something about the world using your code, whether it's numbers or we'll learn about lists on Monday or whatever it is. You can represent all kinds of stuff in the world using your program, but that means that like lines of code have to correspond to stuff that you're trying to represent, and it takes a little while to get used to that, but you'll get better at it in time.
There's a question in the chat that asks, do we go all the way down to 6.2, sorry, to 6.1, or do we stop at 6.2? And you can see here that to get to that last line here, we have to do 6.1. So we go all the way down to 6.1. And you can also see the base case is that when n is equal to 0, n is less than 0, which means we've gone sideways somewhere, and m is 0. Yeah, so the base case when you stop is either n has gone to 0 or m has gone to 0, in which case there's nothing to do. And so the m equals 1 does in fact get partitioned in the recursive call.
Yeah, so you go from 6.4 to 2.4, but you also go from 6.4 to 6.3, and that goes to both 3, 3, and 5, and 6.2. Oh, man, I should draw it out.
It's way too early for this, man.
But the point is, like, there's all these different options, and they both happen each time. And so you go from 6.4 to 6.3 to 6.2 to 6.1 to 5.1 to 4.1 to 3.1 to 2.1 to 1.1 to 0.1, and then you finally like have built this last example. But it takes a bunch of recursive calls to even count one of these, but you're making so many that you count them all.
So there's another question here which I like, which is, could we have done, so in your with m example, you said, well, we can't really do 2.4, this is basically 2.2. So could we have done n minus m, n minus m for the with m call?
Yeah, that would have worked for this example, but not for all examples. One thing you could do is you could write, I want the minimum of m and n minus m. To say, like, look, if this is getting so small that it's bigger than m, why don't we just use that instead?
Right.
But sometimes it's not bigger. In 6.4, it turned out it was. If this was 15.4, then after using 1.4, you'd be at 11.4. But you don't want to make a recursive call on 11.11, because then you're using parts that are bigger than size 4, which is where you wanted to start. So this would be a perfectly good alternative version.
Or 0 plus.
So remember, first of all, so I think you're asking about the return in the else clause, yeah?
Yeah.
Good. So we're asking about the return in the else clause. Now remember that return has to be evaluated every single time we call count partitions, right? There's not just one return here. There are multiple returns, right? So why? So let's do the first call to close count partitions. What do? You call count partition, that's the first line there with m. There is a promise to come back, yeah, and do the without and then the return. But you can't do that until you finish the with. So you go off and you do a bunch of recursive calls. Eventually it will hit a base case and return. And then you'll do the without, it'll do a bunch of recursive calls, eventually hit a base case and return, and then you do a return. So there isn't just one return, there is the return of everything that is being built up. Yeah, and that's why you get all the outputs, not just that last one with the 1, 1, 1, 1, 1.
Should we do something a little bit fun? We could use a decorator to see exactly how it works. And
yeah, I was about to ask. I think we should use a decorator.
Illustrate exactly right. What Hani just described. So, well, let's call it trace. So we'll trace a function by creating a new function that takes n and m, and it's actually going to get the return value of calling that f on n and m, and then it's going to print what happened. So this is going to print f. That's just to get the name count partitions, and then we had an m, and then we had a m, and then we had what it returned. And what did it return? Result. Okay, I'm sure there's a better way to write this, but we've done what we've done. Return G. And we actually do need to move this up here so that we can use it. And I really need to make it a little wider so it doesn't look so weird. Get my picture out of the way. And then we can trace this. And then we can try to look at what happens when we call count partitions on 6 and 4. It crashes.
I think you've got, you have to convert, yeah.
Well, that's a long
that
line.
is a miracle if that ran.
Why did it crash now?
You've got another, result is an int.
So there are more compact ways to build a big string, but we haven't taught you about them yet. So.
You've got to return none somewhere. Yeah, there it is.
Okay, we finally made it. Okay, so here's what happened, is that count partitions actually returned 9 when we called it on 6 and 4. So this expression actually came up with 9 at the very end. Why did it come up with 9? Well, it came up with 2 for this, which are these two, and it came up with 7 for this. I didn't list them all out, but you saw them in the picture. And that 7 came from calling count partitions on 6 and 3. And where did the 2 come from? Well, long ago, we called count partitions on 2 and 2, and that's how we got the 2. And so it added, that 2 and that 7 together to get this 9. How does it keep track of all this stuff? Well, that is the mechanics of the programming language. How call expressions work is that they don't return until they have all of the values that they need to compute, and then can compute the return value and then returns that. So this thing is doing a bunch of work in order to find out that with m is 2, making a bunch of recursive calls after that to figure out that without m is 7, and then finally adding 2 and 7 together and returning 9. And these are all the different calls it makes. Yeah, go ahead.
Yeah, whether we had recursion or not, imagine that with m and without m just called some other function, not recursively. It would make total sense, right? With m, call some function, you get a 2 back. Without m, call some function, gets a 7 back, and then we return the sum of those 2. That's fine, right? All that's happening here is that in order to get that 2 and in order to get that 7, we're calling ourselves. But there's no problem with that, because what John just said is that the Python interpreter has state, has memory. It knows that it has to, after the first call, return the sum of with m and without m when count partition was called on 6 and 3. And so it has to go do all the work it needs to get with m, recursive, non-recursive, don't care. It has to go do all the work to get without m, recursive, not recursive, don't care. And then it slams them together. And then the beauty here is that, okay, to get the with m, I had to do sort of a subversion of the problem. So then I had to solve exactly the same thing, but there's no conflict with the original call, because that's in a different environment, if you will. And so it's doing its own little thing in its own little environment. When it's done, it finally pops back out to the other one.
The next question was, how do you get to count partitions 0, 0 when only one of n or m is being decreased at any given recursive call?
But they're not, right? So the with m is decreasing n, and the without m is decreasing m, right? Which means they're both getting decreased, right? Because in the recursive call, so let's do the with m, yeah? So with m is going to make a call to count partitions with a smaller n. Do we agree on that? Good. That means that the pair of recursive calls for that call will both have a smaller n, right? Don't confuse this second n here in without m with the original n. It's now the n from the recursive call, which is smaller, yeah? And then with m makes another recursive call, decrementing n even again, and then it goes down. So that you have to remember that those n variables are with respect to the recursive call, not the original call, in which case, of course, it would always be the same, but that's not the case.
I see. Yeah, okay, yeah, that makes sense now.
Good.
So just to finish this up, I added a little bit more trace, which says what happens when things get called. And first we call it on 6.4, and that calls it on 2.2, and that calls it on 0.0. And then finally something gets returned. So you can see that, like in the recursive call, n is now 2 and m is now 2. And so it counts count partitions on 0 and 0. in the second time around. And so we see that call. And that call is a base case. And so we find there's one way to compute 2 using parts up to size 2, where you actually use a 2, which is just 2. Okay.
So if this example is extremely confusing, and it's understandable because of the tree recursion, so what I would suggest is go back to one of the examples that doesn't have tree recursion, that just does a simple, like the factorial. Yeah, and make sure that you really understand that, how every time you make the recursive call, you're reinstantiating the local variables and the parameters. And once you've really got your handle on that, then the tree recursion, because the tree recursions are a little tricky because you got to sort of build out these trees. By the way, the absolute right way to follow these recursions is not the environment diagram, by drawing the tree, right? So sit at the root, make a call to count partition with n and m. Before you do anything, put the promise for the 2 things you have to do. I have to make a call here, I have to make a call here. Okay, what does this one have to do? I have to do 2 calls, 2 calls, 2 calls. And you'll see the diagram, and then you should be able to trace the order as John did in the lecture.
Yeah, keep in mind that the environment diagram is going to have as many frames as we have calls here. So it's going to be just absurdly large.
Right, and that's why the tree diagram is a little bit easier to see, because it's you're not lugging around all that extra stuff.
And I would also say that this trace, while it's interesting to kind of watch what's happening, tends not to be that useful for writing the program or understanding how the program works. You really have to think abstractly about what's in here, like what are these going to do, what are you going to get back, and what happens when you add them together.
The next question was, could you explain why you added min n minus m m earlier on in this Q&A?
So the question is about the min function in the with m. You don't actually need that. The reason we put that in there is in this particular example with 6-4, the first call would be to 4, what was it? Let me see if I can get this right. 2, 4. In which case, you don't need the second term to be larger than the first term. And so I'm pretty sure if you run like this, everything will run just fine. It'll just hit the base case.
Yeah.
So we just put that min in there because it sort of dealt with the case when m, the second number, is greater than the first number, which of course doesn't make sense because you can't get to 2 using a 4. It doesn't do any harm. It's just sort of unnecessary.
But this is something that's very problem specific. Like it's the fact that you can't build up a number using a sum using parts that are bigger than that sum is basically why that min is there. It's not something that's like a general fact about writing recursive functions in general or something like that. It was very problem specific.
The next question was, what would count partitions 2, 4 do?
So let's think about it a little bit and we'll run it. 2, 4 says, how do you make 2 out of sums? And there are 2 ways. You could have just 2 or you could have 1 plus 1. So this should return 2. And
Fingers crossed.
that's what it returns. So it's finding one way to do it with a 2, which is just 2. It's finding one way to do it without a 2, which is 1 plus 1. That's the recursive call 2, 1. And then it counts both of those.
So now the question is, what would happen if John changed count partitions 2, 4 to 2, 2? Same answer, right? So what's going on here? Well, yes, the second argument was 4, but you can't use a 4 to get to a 2, so it ignores it. And I can't use a 3 to get to a 2, so I ignore it. So the last number can't be greater than the first number. And that's what the min there was there for, is just to sort of make that explicit. But it doesn't harm to do it. It's just that you won't be able to get to it. All right, any other questions? I want to reemphasize something that was said is don't get frustrated at the recursion. It takes time. It's one of these, it's a little weird. It's not like the loops, which are really straightforward, or the conditionals and all that. It takes a little time. You have to sort of think a little bit different. By the way, back in the day, we used to start by teaching recursion. The first day of class, John and I were just talking about this the other day, is we don't teach you about iteration. We don't do anything. We just teach you recursion. In some ways, that's excruciatingly painful, but it also, in some ways, is easier because you don't have this sort of iterative construct to think about. I think we're doing it the right way, bringing it downstream a little bit, but it's okay. These will take a little bit of time to get your head around how these things are working.
Well, yeah, a lot of people used to drop after lecture 2, and this was a lecture 2 example instead of a lecture 9 example. But still, in this course, we teach this much earlier than most other universities. I think it's a great way to get used to the idea of functional abstraction and to see the kind of problem-solving power of just writing simple functions and letting the computer do the work for you. But it's not easy at all. All right, we'll be back to answer your questions at 2:10 p.m. If you want to join for the unrecorded Ask Us Anything session then. See you soon.
I thought you were going to say unhinged, but okay, unrecorded is fine with me
Also
too.
might be unhinged.
Thanks, everybody. See you this afternoon, hopefully.